Continuing on with this example here, so we've got, let me reset my timer, I don't want to forget this time. Okay, good. Alright, so continuing on with this example. Again, I'm trying to find this unknown density of this fluid here. Okay? Now, I can't just take a sample of this fluid and measure the density that way. I'm going to have to figure out another way to find this density. Well, I do know that it shows up as a variable in this expression where we say, well, P1 minus P2, or P2, we wrote it this way. We derived it as P2 minus P1 is equal to the density times gravity times Z1 minus Z2. Now, here's the thing. We derived this between the pressure between location 1 and 2 for the same fluid between those two. Here I've got something different. This equation wasn't derived for this scenario. So I'm going to have to use this equation, I'm going to have to change some things. But here's the thing. I know there's a density in here. I know some of these pressures. I know some of these elevations. I think I can use this equation, but I can't use it directly because I've got more than one column of fluid. I've got different densities here. So this expression was derived for the pressure difference between one column of fluid. So, but here's the thing. I'm writing 1 and 2 here. You could call this A and B. And maybe that makes more sense, right? So the pressure difference between point A and B is equal to the inverse of, or the opposite of the elevation change between the two, multiplied by the density and gravity. The point here is these subscripts are whatever you need them to be. In this case, I've got 3 surfaces here. I've got surface 1, 2, and 3. I've got a fluid between 1 and 3, and I've got a different fluid between 2 and 3. So I can only use this equation between one column of fluid, the way it's written. So I need 2 equations because I've got 2 columns of fluid. Now, to use this equation, I do need to know, before I move over, I do need to know my z values. So let's say that I've got a Z3 down here. I've got the elevation of surface 1, Z1, and then up above here, I've got Z2. Now I think I'm going to set this one equal to 0. You could set any of them equal to 0, or you don't even have to set any of them equal to 0. Just understand everything above this point is greater than this value. So if I set this as 0, everything above it's going to be positive. Anything below it's going to be negative. So Z3, the lowest point, if I set that 0, then Z1 right here, which is 5 meters above that, Z1 is a positive 5 meters. And Z2 is 8 meters above that, so that is a positive 8 meters. Now, Steve, how the heck does that help us? Well, again, this expression will get us through one column of fluid with one density. I've got more than one column of fluid with more than one density, so I just need more than one equation. So here's what I can do. I can say, well, I've got the same fluid between points 1 and 3. So I can say, well, P3 minus P1 is equal to the density, in this case is water, because it's water from 1 to 3, times gravity times, and if I've got 3 minus 1 here, this needs to be Z1 minus Z3 there. Now, I've got this unknown fluid between 2 and 3, so I could say, well, P3 minus P2, and I could write that in either order, by the way. I could say P2 minus P3 there. It's an unknown fluid between 3 and 2, so I'm going to subscript that density, that rho, with a U. So it's the unknown density times gravity. If this is 3 minus 2, this needs to be 2 minus 3. Again, we've derived this equation where Z represents elevation. So as I increase Z, pressure decreases. All right. What do we know here? So here's the process. Identify what you're looking for. Identify fundamental expressions that might get you to a solution. Make sure you've collected all the given information. Now I know that I can say, well, Z1 is equal to 5 meters and Z2 is equal to 8 meters, right? And I'm going to have to assume, I'm going to have to make an assumption. I'm going to have to assume the density of water, and we're in metric units here, is going to be about 1,000 kilograms per meters cubed. I'm going to have to make that assumption because they didn't give it to me. If they want you to make another, if they want you to assume another value, they will give you a value for it. Okay? Okay. Now, so again, the process is, what are you looking for? What do you know? What is the fundamental expression you can use to try to find it? Simplify that to your particular situation, and then count the number of unknowns. Do you have as many unknowns as you have equations? Well, I don't know. I don't know P3. I do know P1 and P2. That's known. I know the density of water. I know gravity. And I know all the z values. I don't know the unknown density, and I don't know P3, but I've got two equations, two unknowns. The engineering work's done. Now it's just algebra. Right? And the way I try to grade is I try to get you, if you get to this point where you show me you know how to solve the problem, and you've got as many equations as unknowns, and you've identified all of the properties needed, you made any assumptions needed, I try to get you to 80% of the credit on this point. Right? I try to get you to a low B at this point, because you basically show me you can solve this problem given an infinite amount of time. You've identified, our goal here is to teach you the fundamentals associated with these problems. I'm going to assume you can do algebra and units on your own time if you have time to really get it checked. To get an A, you're going to need to do the algebra and the units. So let's see if we can get to an A here. All right, so again, I don't know P3, but I don't need to know P3. That's the thing, is I don't need to know P3. I could say P1 plus the density of water, gravity, times Z1 minus Z3 is equal to P3. And I don't need to know P3. I'm going to solve around it. I'm going to say that's equal to P2 plus the unknown density times gravity times Z2 minus Z3. So I've solved both these equations for P3 and set them equal to each other. And now you can just write one big equal sign. Also note that P1 is equal to P2. They're both open to the atmosphere. So anytime a surface is open to the atmosphere, you can assume the pressure at that point is 1 atmosphere, unless they tell you another value. Right? And they didn't tell us another value in this problem, so we'll just assume it's 1 atmosphere. So it's here and it's here, so that goes away. So algebra says that I'm left with the density of water times gravity times Z1 minus Z3 is equal to the unknown density we're looking for times gravity times Z2 minus Z3. And that's one unknown. The unknown density is equal to, the gravities are going to go away. It's the same gravity on both sides. It's 9.81 meters per second squared, but we don't need the numerical value. That's going to be, I'm going to rewrite it this way. I'm going to say Z1 minus Z3 divided by Z2 minus Z3, and that's equal to the density, or multiplied by the density of water. Z1 we said was 5, Z3 is 0, so this is 5 minus 0 divided by, this is 8 minus 0, so that's 5/8 the density of water, which we can say is 1,000 kilograms per meters cubed. 5/8 of 1,000 kilograms per meters cubed. I think, double check this with your calculators. Most of the time the math is not this easy where I can do it in my head, but I think that's 625 kilograms per meters cubed. That's your answer. This is what I'm most concerned with. Can you get to this point where you know you've got as many equations as you have unknowns, and you show me you know all the unknowns to get there? Okay? Or you go look up the unknowns that you don't know. Get it down to a point where you can solve it. Solving it, that's important, but that's not as important as getting to the point where you can solve it. This doesn't matter if you can't get to this point. Okay? So a nice organized fashion where it's easier for me to award you partial credit if you set it up in a nice organized fashion. You don't have to follow my format, but if it helps you, please do. Set your givens over here to the right. Draw a diagram of the picture from your book. If it doesn't give a diagram, draw a rough sketch. Identify what you're looking for. What are the fundamental equations you're going to use to find it? Set it up, and then do your algebra. Notice I didn't plug any numbers in until I got to the end. You plug in numbers as soon as you're ready. Right? If you don't want to carry around a bunch of variables, that's fine. You can plug in numbers back here. I would suggest to you you're going to do a lot more writing that way than if you wait till the very end. Notice I didn't care, if there's some other methods for doing these kind of problems. There's like a method that says, well, if you want this pressure, You start at this point, you add this, and you subtract that. And that works if you want to memorize all that and figure it out, and that's okay. I don't mind that if that works for you. I don't do manometer problems often enough to get that right every single time. I can get this right every single time. I can set up one equation for this column of fluid. I can do that right every time. I can set up one equation for this column of fluid every single time. If there's another column of fluid, I can set up an equation for that one. And then I can splice those together using algebra. I can do that correct every single time. And here I don't have to worry about the signs. The signs are taken care of over here. This is 0, everything above it's positive, anything below it's negative, and then I'm just plugging in z values into these equations. It's whatever works for you. If you need help with the other method, I can try to help you. I've done this enough times that I can probably walk you through it, but I find if I explain it to you this way, this works for most people. And then you'll probably figure the other simplified methods out on your own if that's really what you want to do. Okay. Where are we at for time? You know what? I'm going to stop us there. We'll pick up the next video there with the next. We'll pick up the next video from there. Okay. It's a little short on this video, and that's okay. Let's see if we can get the other example in the next video. All right. We'll be back.